In this lesson, we're going to talk about SN1, which is one of the first mechanisms you learn in organic chemistry. Understanding this mechanism and comprehending the reasons behind how this reaction occurs will lay the foundations for success in all future organic chemistry reactions. Chemistry happens when electrons move. Electrons are what make reactions happen. There may be a deficiency of electrons, and you have a positive charge. Extra electrons yield a negative charge. An unequal distribution of electrons between two atoms makes the bond polar. Understanding organic chemistry will teach you, conceptually, how and why electrons move, and you can apply this to many other fields of chemistry, especially biochemistry, biology, medicine, and drug design. So strap in and get ready for one of the first big reactions in organic chemistry. In order to approach substitution reactions, we have to review the four arrow-pushing mechanisms. These are nucleophilic attack, leaving group leaving, proton transfer, and carbocation rearrangement. A nucleophile is something that loves a nucleus, or is attracted to positive charges. Phile comes from the Greek word root philos, the same as Phil in Philadelphia. It means love, just as Philadelphia is the city of brotherly love. So, a nucleophile is attracted to positive charges. Since opposites attract, it would make sense that nucleophiles are negatively charged, or have a free electron lone pair, as electrons are negatively charged. Notice that the butt of the arrow in this mechanism is drawn from where the electrons start, and the head of the arrow points exactly where they end, at the positively charged center. In this example, the substrate, the molecule with 4 carbons, has a positive charge, as is always the case in SN1 reactions. It is an electrophile, which means it loves electrons or attracts negative charges. So, something fully or partially negatively charged, a nucleophile, wants to be united with something fully or partially positively charged. That's the idea of nucleophilic attack. A leaving group leaving is as simple as it sounds. Here, Lg represents a generic leaving group. The bond from the carbon to the leaving group is severed, and the leaving group leaves. Notice that both electrons from the bond travel in the same direction. The electrons go toward the leaving group, making it negative, while the substrate becomes positive. A proton transfer is also quite simple. An H plus changes hands. Protons are traded quite easily in the chemical world. Notice that there are still arrows showing how the electrons flow. They flow from the lone pair to the hydrogen. All electrons need to be accounted for. They have to have a starting and ending location. Charge needs to be balanced. The left side of the equation is neutral overall, so the right side needs to be as well. Positive 1 and negative 1 together add up to 0, which is neutral. The fourth mechanism is carbocation rearrangement. Stability plays an important role here, which we'll talk about soon. For now, notice that the butt of the arrow is drawn from the middle of the bond. This represents the electrons. The bond is always drawn from where the electrons originate. Here, the arrow points toward a positive location, and the electrons, with the methyl group in tow, move there. This is a carbocation rearrangement, which can be tricky. We'll see an example later. So, you've heard an explanation for the 4 arrow-pushing mechanisms. What is SN1? SN1 stands for unimolecular nucleophilic substitution. Let's break that down. Substitution is when one thing is replaced for another. That's simple enough. Nucleophilic is just a spin on the word nucleophile. We're definitely going to see the nucleophilic attack mechanism from before in SN1. Unimolecular simply means that only one molecule is involved in the rate-determining step. There may be many steps to a certain reaction, some with multiple molecules, atoms, and ions, but if this reaction occurs via an SN1 mechanism, the slowest step only involves one molecule. Let's dive right in and do an example. Here's a molecule. Notice that it's all carbons and hydrogens, except for the one functional group, which is bromine. Often, the first step in analyzing what to do in an organic chemistry problem is to identify the functional groups. Notice how the mechanism is drawn. First, the carbon-bromine bond is broken, and the electrons go to the bromine. This leaves the bromine with a negative 1 charge, and the carbon with a positive 1 charge. Then a nucleophile appears, OH-, which attacks, with the electrons coming from the negative ion and attacking the positively charged carbon, yielding the final structure, where the carbon has 4 bonds once again. This is SN1. The key unimolecular rate-determining step is when the leaving group leaves. Okay, that's nice and all, but why is this happening? What tells you whether an SN1 reaction will occur? The most important part is the structure of the substrate. Here are 4 similar structures, each with the same leaving group, arranged in order of increasing number of R groups. In this case, the R groups are all methyls, but they can be any alkyl group. The greater the number of alkyl groups, the more likely it is that the substrate will react in SN1 reactions. Thus, tertiary substrates are more reactive than secondary, which are more reactive than primary and methyl. Recall that the leaving group leaving is the rate-determining step of SN1 reactions. Anything that can speed up the slowest step will make SN1 favorable. That iodine won't leave on its own from methyl and primary substrates, so SN1 won't occur. It's best on tertiary substrates. This is something you need to memorize. You can repeat and burn these reactions into your brain. To be honest, much of this is necessary for organic chemistry, doing a large number of problems to see the concepts from a variety of different angles. But understanding the why behind this is extremely important. Tests won't all be spilling information onto the page. You'll have to apply the concepts you learned. So if you understand the reasons behind them, you'll perform better on the exam. If you can fit these reactions into a particular context, they'll be easier to recall, since you'll know where in your memory to look for them. So, why do SN1 reactions occur best with tertiary substrates? There are 2 layers to this answer. The first is that tertiary carbocations are the most stable. Carbocation stability helps drive the reaction forward. If the product of a reaction is stable, the reaction is more likely to occur. A tertiary carbocation is much more stable than a primary carbocation, so the leaving group is more likely to leave due to the stability of the products. Why is a tertiary carbocation so much more stable? Let's compare a tertiary and a methyl carbocation. In the tertiary on the right, the neighboring alkyl groups actually donate electron density. That positive charge is strong, and it's able to pull in some electron density from the alkyl groups, which are willing to donate it. Hydrogens don't have much electron density to donate, so they can't help stabilize the carbocation. But alkyl groups can do this, as they have a lot more electrons, so more electron density can be drawn in to stabilize the carbocation. I want to be clear, this is still a fully +1 positive charge. This stabilization allows us to survive as an intermediate long enough to be attacked. Finally, let's talk about SN1 nucleophilic attack. There's one more important aspect to how SN1 works. When the leaving group leaves, the substrate changes from tetrahedral, an sp3 hybridized carbon, to trigonal planar, sp2 hybridized. This means that it becomes flat or planar. Check out the 3D images. Before the leaving group leaves, the bromine on one side blocks access to the central carbon, and on the other side, there's a lot of steric hindrance from the methyl groups crowding the way. Steric hindrance is a term that means just what you're seeing, other groups crowding the site of attack. After bromine leaves, the structure becomes trigonal planar. It looks the same on both sides. So when a nucleophile comes along, it can attack from either side. There are no groups sticking out blocking the entrance of the nucleophile. There's an equal likelihood of nucleophilic attack occurring from the top or the bottom. Now let's bring it all together with one more example. Here's the molecule. It has a chiral center. OH is a bad leaving group, but with a proton transfer, it becomes a great one, as H2O is quite stable, and when it leaves, it becomes a neutral molecule. Then there's a secondary carbocation, and carbocation rearrangement happens as the methyl group shifts. This converts the intermediate from a secondary to tertiary carbocation, increasing the stability. Then the nucleophile attacks. The chloride ion can attack from either the top or the bottom, since the carbocation is trigonal planar, as you saw before in the 3D images. The products are a 50-50 mixture of configurations on the chiral carbon. That's SN1, folks! A great introduction to reaction mechanisms in organic chemistry. Hopefully, understanding some of the why behind how this occurs will help you internalize the information and be able to apply it on exams and future problems.